Hi, I am team captain of UluRover. We founded this team in 2023 where we made our first prototype called Hedger. Then in 2024 we participated in ARC and we secured 8th position. Now I am excited to announce that in 2026 we are again coming to ARC with the 4th generation of our rover which we call as Asteroid Destroyer. Our team consists of 5 sub-teams including mechanics, software, electronics, science, and organization. And all of them are led by a group of students coming from different departments like sciences, engineering, and social sciences as well. The goal is not just to build it, but also to learn from it. Now, let me introduce you to my team and my beast, UluRover's Asteroid Destroyer.
Hi everyone, my name is Mahlit. I'm the organization team leader of UluRover.
As the organization team, our role is to keep everything running smoothly behind the scenes. We plan and coordinate weekly meetings where all teams come together, share progress, and align on next steps. Staying organized is key for us, so we actively use tools like Notion and Google Calendar to track our tasks, monitor progress, and make sure we meet important deadlines. We also make full use of our university's workshop where all the ideas come to life. It's where collaboration turns into real, tangible work.
I am Batu, I am the captain of the mechanical team and I have designed the robotic arm.
The robotic arm we designed, it has 5 axes. Skeleton of the robotic arm mostly made of aluminum and some part made of plastic and steel. The weight of the robotic arm around 25 kilograms. It can reach around 1 meter area. We use step motor on all axes to move the arm. It could make arm heavier but we can't take too much torque from step motor. And for the power transmission we use worm gear we produced. Worm gear help us that robotic arm can stand continuously even when we cut the electricity. On the top of the arm, there are grip and drill system. We can use one of them we want thanks to system we designed.
For UluRover's mobility system, we decided to go with the rocker buggy suspension system with 6-wheel full electric drive. We decided to go with the rocker buggy suspension because it allows us to maintain constant contact with the ground and allow us to never slip. Now, we do this with a central shaft. The shaft is connected to both suspension arms that move separate ways. Now for the wheels, each wheel has a built-in DC motor with 33 Nm of torque. This allows our rover to climb steep angles and overcome the kind of challenges we may face on the Arc 26 environment. Weighing it at almost 35 kilograms, the movement system is the main body of our rover. The movement system alone has a volume of 97 by 105 by 38 centimeters cube. Now, the entire system is made almost entirely out of aluminium, except for the gears, shafts, and the wheels.
Greetings, I am Eren, and I will be introducing you UluRover's electronic and communication architecture. At the core of our system, an STM32 manages real-time movement. It drives the BTS series for our mobility system and utilizes TB66-100 and DM860H drivers for the stepper motors. By executing trapezoidal motion profiling and PID algorithms, it ensures smooth acceleration and precise positioning. For high-level tasks, we rely on Jetson Orin Nano, which handles autonomous navigation and image processing via the Z2 camera. Regarding communication architecture, our data link uses ubiquity transceivers on the 5 GHz band to prevent interference. This connects via Gigabit Ethernet to the Jetson or Nano, handling tasks like Z2 streaming and ROS2 messaging. For manual operation, we utilize a 2.4 GHz radio link system. Also, we are in a strict compliance with national radio frequency regulations, limiting our power at 27 dBm.
Hi, I am Samet. I will talk about the rover's power system. The main power users in the rover are the DC motors for movement, the stepper motors for the robotic arm, the MinLab system, and the Jetson Orin. They need different voltage levels. To supply this power, we designed a custom PDB. It provides 4 different voltage levels and includes fuse for safety. We use a 24-volt, 18 ampere hour LiFePO4 battery, which allows the rover run for about 1 hour and 30 minutes. This system provides stable power, enough capacity for the mission, and a safe design.
Hello, my name is Sid, and I am going to tell you about our UluRover's safety features. UluRover features a modular driver that is easily removable for quick maintenance. Also, we integrated indicator LEDs and an emergency stop button to immediately stop the system if there is a problem. Based on our power calculations, we are using specifically selected cables to ensure safe power distribution.
The goal of the UluRover science team is to provide a solid, foundational scientific hypothesis to serve as the basis for the rover's activities and design. And this year's new and improved mini-lab design does just that.
The mini-lab is a Raspberry Pi 5 and Arduino-controlled automated system weighing just 2 kilograms and measuring 45 by 15 by 30 centimeters. This compact, modular platform enables low-contamination sampling, storage, and testing while integrating the drill, chemical analysis, caching, and a weather station into a single, remotely operated dashboard.
Our sampling system uses a 3D printed PLA drill capable of reaching depths of up to 30 centimeters. Mounted on a rotatable mechanism on the robotic arm, it enables precise collection from multiple angles and delivers samples directly into the mini-lab. Once collected, soil enters a custom split funnel system that separates each sample into major and minor portions for parallel testing. The minor portion supports gas evolution assays with sensors positioned above it, while the major portion is mixed with water so dissolved ions can be distributed into tubes for 3 color change tests.
A rotating drum with capacity for 9 test tubes and 1 rack moves samples in front of camera for imaging. This allows the visual output of all color change ion tests to be monitored in real time from base through the mini-lab dashboard. The same camera is also used to photograph rocks for identification and geological analysis. To complement this, we developed an in-house PyTorch-based rock identification model trained on a created dataset of region-specific rock type, with accelerated onboard processing supported by the Raspberry Pi AI chip. The rover also includes an onboard weather station mounted at the highest point of the system, its antenna. This station continuously measures key atmospheric gases using MQ sensors, including hydrogen and methane, along with UV levels, atmospheric pressure, and temperature.
Together, these systems allow us to test a wide range of life detection hypotheses centered on the past or present existence of microorganisms on Mars. Over years of designing Mars-focused science missions, we found that our hypotheses consistently follow the same core logic. Test soil for habitability-associated ions through color change chemistry, support those findings through identification of rocks likely to contain those ions, and test for organic molecules through gas evolution assays such as hydrogen peroxide reactions, especially targeting compounds associated with microbial metabolism. By automating this workflow in a modular mini-lab with interchangeable chemical assays, we can rapidly adapt our science strategy from one competition to the next, whether the focus is methanogenesis, sulfur reduction, or another microbial pathway.
My name is James, and I'm the captain of the software team, and I'll take you through how the autonomous navigation works.
We have continuously improved from the last previous years, and we have improved our algorithm. And this year, we are using ROS2 as our operating system and Z-Mini as our sensor. Our pipeline follows a see, think, act loop, and it is divided into 4 parts. Perception and fusion is the first one, in which we use a Z-Mini camera and extended Kalman filter to fuse visual odometry with IMU data, which ensures that it will stay stable even in rapid movements. Then we have mapping and localization, in which we are using RTAP map, which generates a 3D cloud, which then we project into a 2D cost map, while AMCL uses the particle filters to pinpoint the robot's current position in that environment. Then we have path planning. For path planning, we are using the ROS2 NAV2 stack, which coordinates the global trajectory planning and use a local controller to dynamically navigate around the obstacles in real time. Then we have the feedback, in which we are using high-level commands translated via the differential kinematics to STM, which execute PID motor control and feeds the encoder back into the loop.